Hello everyone, I am Linendra Surve. Welcome all of you in the lecture series of vibration control based on University of Mumbai. We are gone through dynamic vibration absorber, dynamic vibration neutralizer, and we have taken one very good numerical on dynamic vibration neutralizer. Again today we are going to discuss a good quality numerical based on dynamic vibration absorber, or you can say neutralizer. So look at the question given itself. This is the entire question, and if you try to solve this kind of questions, it is very easy for you if question asked on this module. Okay, so this question can contain all the required essential data. If you solve this kind of design, then it is very easy for you to solve the questions from this module. Okay. So the vacuum pump of electron beam, the previous example we have taken for air conditioning plant, and similar kind of this question is again, but the change is vacuum pump is given here. Okay, and little bit change in the question. You can see part 1 and part 2. The little bit change is over there, and how we can solve for that also we can going to discuss. A lot of students are asking me these questions, so please give the solution for this question, and we will discuss entire solution today. Okay, so vacuum pump of an electron beam setup is schematically shown in the figure. So in a question itself they have given figure. I have not plotted a figure because not required in this. Whenever we will require, we will discuss in that section only. Okay, the pump is mounted on the springs. So your pump is mounted on springs, and vertical unbalanced force of frequency, that is omega, equals to rotational speed of the pump generated. So omega is the rotational speed of that pump is generated. The amplitude of force is a 50 Newton. So this is an additional data. This data is not present in the last numerical that we have solved. So this is a newly data given. So we will consider that is the amplitude of force is 50 Newton and the normal working speed of the pump, which is 1500 rpm. So this is the normal working speed of that pump, and that speed, the amplitude of the force is given as a 50 Newton. The pump body is found to be resonate at this speed. So particularly this speed, our pump body is going to be resonate. Okay. To control the vibration of pump body, it is proposed to attach a neutralizer. Okay. So why we are introducing neutralizer? See here. To control the vibration of pump, that is important line. To control the vibration of pump, we are introducing a neutralizer. This neutralizer should be tuned to 1500 rpm. Again, tune rpm for this neutralizer is 1500, and should be so designed that it satisfies the following constraints, and some constraints they have designed, and that constraints it should be followed. Okay, or satisfied. The resulting natural frequency of a combined system should outside the range. So this is the range is given. Whatever is the combined natural frequency of a resulting system, it must not lie inside in this range. It should be lies outside in the range. Okay. To take care of possible vibrations in the pump speed, the available rattle space for the neutralizer mass is such that its peak to peak amplitude or movement. Okay, that line is very important. Peak to peak movement should not exceed 15 mm. So we need to take again this constraint also while designing the mass of neutralizer. Peak to peak movement should not exceed 15 mm, and this 15 mm is very important with respect to this 15 Newton. Okay, so force amplitude is 15 Newton and peak to peak movement is a 15 mm. Within that limit, you need to design such a neutralizer or adopt such a neutralizer that having a mass in kg. How much is the mass in kg? Before, the neutralizer of mass 0.1 kg tuned to 1500 rpm resulted into two natural frequencies of the combined system. First one is omega 1 is 1400 cycles per minute and omega 2 is 1607 cycles per minute. Determine the required stiffness and mass of the neutralizer. So this is the entire design question based on the dynamic vibration neutralizer, and we are going to solve this Previously, what we have taken that question on air conditioning plant, that is a similar question for this, but the change is in the second constraint only. So how to solve that second constraint and how we can design mass of the neutralizer and how much is the stiffness required if the peak to peak amplitude is restricted to 15 mm and the force of amplitude is given as a 15 Newton. So while designing, we will consider these two newly adopted cases and we will solve this numerical. So we are treating here our pump body on a spring as a single degree of freedom system of effective mass m1. So pump body, we are considering pump body as single degree of freedom having of effective mass as m1. Okay, and this is the given data. You can look out here. Given data is given omega 22, that is 1500 rpm. Pump is going to be resonate at 1500 rpm from the question itself. This data you have taken. Omega 1 is 1400 cycles per minute. Omega 2 is 1607 cycles per minute. This data is taken from the question itself. You have read the question and then you have taken that data. The mass of initial mass of trial neutralizer is 0.1 kg. That is again known, and the range, that range is very important. The range is given 13500 to 1650 cycles per minute. Now how we are going to proceed? We know the end results for these type of questions. Okay, we have solved or we have seen the derivation or we have found out the what will be the end results. There are only two end results or we can say formulas. So for the trial neutralizer, what is formula for the trial neutralizer? We know this formula is omega 1 divided by omega 2 square of that plus omega 2 divided by omega 2 square of this is equal to 2 plus m2 by m1. This formula we have studied. Okay, omega 1, now just we are going to putting the values. What is our omega 1 and what is our omega 2? We are just inserting the values. Omega 1 is given as 1400 and omega 2 is 1500 square of that plus omega 2 value is 1607 and omega 2 value is 1500 resonant frequency 2 plus m2t by m1, where m2t is the mass of neutralizer. M2t is the mass of neutralizer. We are putting m2 is equal to m2t, mass of neutralizer or trial neutralizer. Okay, so after solving this, you will get one expression m2t divided by m1. After simplification, this I am getting 2 minus from this data. You will get m2t by m1 is equal to 0.01866. Those are new comers for this video. I will suggest you go and watch the previous video or previous theoretical video and one numerical video based on this dynamic vibration neutralizer. Then you will understood what is this formula, what is its end results, from where we have taken these end results, and it is easy for you then to solve this numerical. So this is our equation 1. Okay, so in equation 1 we have found out m2t divided by m1 is equal to 0.01866, the mass of, where m2t is the mass of neutralizer. Now frequency calculation. What is frequency calculation? We have one formula, that is omega 1 omega 2 divided by omega 2 bracket square is equal to 1. This frequency formula is known. Okay, now here we are considering f1. If our f1 is 1350, okay, we will proceed with if my f1 is 1350 because the range is given I will find out what will be my F2. So F1, if I put F1 is equal to 1350 cycles per minute. Okay, so if I putting F1 as 1350, this is omega 2, or I can use here replacing omega 1 as F1 and omega 2 as a F2 divided by omega 2 2. Omega 2 2 is nothing but 1500. Square of this is equal to 1, and from here you will get F2 as. After simplification, this is nothing but frequency calculation. Again we are using end results or formulas. This is the end result we have seen in dynamic vibration neutralizer. Product of the frequency divided by combined system frequency square is equal to 1. That end results we are utilizing over here, and we are finding out what will be my final frequency F2. So final frequency comes out 1666.7 cycles per minute. So this is my final frequency, and again you can see here the final frequency whatever is the obtained here, this is out of the range. The frequency is outside the range. Our range is given as 1350 to 1650, but obvious our frequency obtained is outside the range. So we can mention here this is acceptable frequency. This frequency is our acceptable frequency, because this is not lies inside in the range, it lies outside the range. It lies outside the range. What is range? 1350 to 1650. So this is acceptable because lies outside the range. So this is our range, cycles per minute. So this is a very good understanding for you. If you understood this phenomena, then it is very easy. Range is given, and whatever is the frequency that should be lie outside, then and then only it is acceptable. You can see once 1666.7, which is higher than this range or lies outside the range, so this value is acceptable. Now what will happen? If we go through our final frequency? If we go through our F2 as, if I go with F2 is equal to 1650. If I put my F2 as 1650 cycles per minute, what will be my F1? So this frequency calculations, again we are doing frequency calculation, we are checking, we are doing trial and error over here. So F2 is equal to, so here I am going to, here is my task is to find F1. So F1 into F2, 1650 divided by 1500. So from here I have found F1 is equal to, so finally you will get F1 as 1363.63 and cycles per minute. Now look at this value, 1363.63 cycles per minute. Okay, this lies inside in the range. Look at the range. The range is given as 1350 and the value obtained for lower frequency is 1363.63. That is nothing but this is lies inside in the range, so this value is not acceptable. This frequency is not acceptable. So which one is acceptable here? Which frequency is acceptable? The frequency we are going with F1 as 1350 cycles per minute, and we are going with F2 as what we are to found out 1666.7 cycles per minute. So from here onwards we will consider the two frequencies. We will consider F1 and F2. We will proceed or we will solve the rest of the numerical based on these two frequencies. This frequency, lower frequency is not acceptable. Which frequency is acceptable? Here F1 is 1350 and F2 is 1666.7 cycles per minute. We will solve the rest of the numerical based on these frequencies. So look at here. We are utilizing this data, F1 as 1350 and F2 as 1667.7. So 13501667.7 divided by 1500 square 2 plus m2a by m1. Here we have assumed m2a as our new mass of the neutralizer m2a. So m2a by m1 we have found out after simplifying this 0.045. Do the simplification and what the equation? This is the equation number 2. What equation 1 we have found out? I have written equation 1 again. M2t by m1 is equal to 0.0186886. So utilizing equation 1 and 2, what we can do, same concept we are using in the last numerical also. Divide equation 1 by 2, you will get required data. So dividing equation 2 by 1, this m1 will get cancelled. M2t divided by m2a is equal to 0.4231, and from here we are utilizing this data given. What is this given data? Mass of the trial neutralizer is 0.1 kg. Initially we have not put a mass of a trial neutralizer 0.1 kg in the equation. We have take that equation as it is. We have simplified over here, and then we are going to put mass of the trial neutralizer as a 0.1 kg. Then what we will get? Mass of the second neutralizer or mass of m2a is equal to what we will get? 0.2363 kg. Now we have to check whether this mass is right or wrong. So for that we need to find out what will be the stiffness. So how we can find stiffness for this data? So for stiffness we know omega 22 is equal to under root k2a by m2a. This formula we are utilizing, simple frequency formula, and omega 22 is nothing but 2 pi n is 1500 2 pi n by 60, square of that is equal to k2a divided by m2a. Put the value of m2a 0.2363. From here omega, so this are 1500 is given in terms of rpm. We are going to convert omega into radians per second. So 2 pi n by 60, square of that, square root will get cancelled because we are doing here square. So k2a divided by m2a we are putting the value of which is obtained 0.2363. From here you will get k2a, stiffness of the trial neutralizer spring, and what we will get k2a is equal to how much k2a value are obtained? k2a obtained as, look at here, 5831.34 Newton per meter, and this is the final answer, the trial neutralizer stiffness of the spring. But we have to check whether our constraints are fulfilling or not. So what is our constraint? So for that we are utilizing now amplitude of neutralizer. We are going to find out what is my amplitude of neutralizer, that is x bar is equal to f divided by k2a. This formula is known. F is equal to k into x, that is nothing but force due to the spring. So spring constant is going to be utilized. Force is given in the question itself. So this, from here onwards we are going to see what the new concept asked in this question. So air conditioning plant question is till here similar. K2a, we are finding out what is my m2a and what is k2a. Till this data we have solved similar fashion as that of the air conditioning plant problem. But in this pipeline problem, now what is changed here? We are utilizing the given data. They have provided force of amplitude is given as a 50 Newton. So this value is 50 Newton. We are checking whether our constraints fulfilling or not, whether our given constraints satisfied or not for given frequency ranges. So 50 divided by k2a. K2a is 5831.34. So how much is the x bar or amplitude of displacement amplitude of neutralizer? That is nothing but 8.57 mm, and this is amplitude of neutralizer. Now one more concept you will require. They have given amplitude of neutralizer, that is peak to peak movement. So for peak to peak movement, look at here. peak to peak movement. So how we are going to consider peak to peak movement? If just consider this cycle. Now if I needed a peak to peak movement, what is my displacement amplitude? This is my displacement amplitude, that is x bar, and again this is my displacement amplitude, that is x bar. Now I needed peak to peak amplitude. Peak to peak amplitude is nothing but this amplitude. Okay, so what is this amplitude? This entire value of amplitude we need to consider. So what is this entire value? X bar plus x bar. So this is nothing but peak to peak amplitude, that is 2x bar. So if I found out what will be my 2x bar is equal to 2 into 8.57, and this is equal to 17.14 mm, which is greater than a given constant. Constant is given as peak to peak amplitude should not be greater than 15 mm, but in the right now condition, peak to peak amplitude is found as 17.14 mm, which is higher than that of a given amplitude. Given amplitude is 15, but obtained amplitude is 17.14. So this value of a stiffness is not fulfilling or not satisfying the constant. This value of a mass trial mass neutralizer 0.2363 kg is not satisfying the given constant. So we need to find again what will be the mass of neutralizer M2A, and similarly we need to find out what will be the mass stiffness. So how to do from here onwards? Look at it. If my peak to peak amplitude condition is not satisfied, so what is satisfied condition? I needed peak to peak amplitude x bar. What is x bar? I needed, that is 15 by 2. So how much is the x bar required? 17.5 mm. So I will proceed with 7.5 mm. 15 by 2, the given amplitude 15 by 2 is required. 2x is equal to 15, so x bar is equal to 15 by 2. Our amplitude, how much we needed? 7.5 mm. Previously, how amplitude we have found out? Amplitude is found 8.57. This is not acceptable value. Already we have seen why, because 2x is greater than 15. So we will try with the given data. We are going to take x bar as a 7.5 mm, and we are going to find out what will be my K2A. So K2A is equal to F divided by x bar. So F is 50 Newton divided by x bar is 7.5 mm, convert into 10 raised to minus 3 meter. So this is a Newton, this is meter. So final answer we have obtained here. How much? Stiffness of a spring 6.7 Newton per meter. Now look at the difference in the stiffness. First stiffness K2 is obtained as 5831.34, and the new stiffness is relating to 7.5 amplitude is peak to peak amplitude is 4 times 6.7, which is higher than that. Means what? For particularly I am saying about this amplitude, this stiffness will be required. Okay, so that's why we are not proceeding with the K2 as a 5831.34, because this stiffness is not satisfying the end condition. Now again I can find what will be my omega 22. From here I can find K2A by M2A. So from here M2A we can easily find, or we can put here 2 pi n 1500 cycles per minute. Square of that is equal to, put this K2A 666.7 and M2A. Ultimately you will get M2A from here. And what is M2A obtained here? That is 0.270 kg. And this is the required answer, final answer. For this mass, we are going to satisfy x bar as a 7.5, 2x bar as a 15, and stiffness, new obtained stiffness as 6666.7 Newton per meter, and this will be my final end results. Okay, so mass of trial neutralizer not be 0.2363, it should be 0.27 kg. To satisfy the second constant, that constant peak to peak movement is 7.5. Okay, now how to validate this data? You can validate whether this data particularly for what will be the new frequency for these masses. Definitely you can validate. So how we are going to validate this? Now look at here. We have just found M2 as 0.270 kg. Now our first equation is M2T by M1 is equal to 0.01866. This is our first equation. From that first equation, what we are finding, mass of trial neutralizer is given. This 0.1 is given. So if we are putting 0.1 and we are solving for M1. How much is the value of M1 we are going to obtain is 5.3022 kg. Again, M2A by M1. We are solving for M2A by M1. M2A 0.270 and M1 is a 5.3022. After simplifying that, we will get M2A by M1 as in terms of ratio as 0.050922. Now we are going to validate our results. In exam, you will not require this. You just solve for here M2A, that is sufficient. No required for validation. But we will see what is our validation. Validation is nothing but omega 1 divided by 1500 bracket square, omega 2 divided by 1500 bracket square plus is equal to 2 plus M2A by M1. M2A by M1 is the new found data. This is newly found data. M2A by M1 we are utilizing over here. And what is the ratio? Right hand side we have obtained as 2.050922. So what will be the new frequencies F1 and F2 or omega 1 and omega 2 to fulfill this newly obtained data or newly obtained right hand side. So after simplification you will get newly obtained frequency omega 1 as 1340 cycles per minute and omega 2 as 1679 cycles per minute, which is lies outside the frequency domain range. The frequency domain range is given 1350 say like 1650. So look at the 1340 is loud outside the range and 1679 is again lies outside the range. So the obtained results are truly correct. So how we are going to validate? The similar manner. So we can say the obtained results or this mass is truly validated with the newly designed system, or this newly designed stiffness is validated, or newly designed mass is validated because obtained frequency of combined system is lies outside the given frequency range. So this is the whole answer or whole detailed solution of this numerical. I hope this kind of question will be asked in university and you can solve these questions with the X. Thank you very much. Subscribe our channel and comment on it.